Good morning, class. Is the audio coming through? Can you hear me?
Yes, sir.
Thank you, Liliana. I appreciate that. I have a big voice, but technology will render it silent really fast, so appreciate that. Okay, I will have another quiz probably posted today. I've got your homework up for this week, and so there'll be another quiz that'll be due at the beginning of next week. You don't have a quiz this week. That's a little breather since you just had a test and give you a little bit of time to work on your homework. So I don't look at that as being, a gift or whatever. It's just that there's only so much you can get accomplished in a particular week. So I appreciate your attention to the test, and I appreciate your attention to staying current with your work. There's a lot of busy work and a lot of computation and theoretical ideas that has to be executed, that have to be executed in this class. And so I appreciate the fact that everybody is taking this task very seriously. Now, what we want to do today is talk about another application. Is called center of mass, or centroids, and this will be the last application that we cover in this chapter. There is a section after this on force due to water and other liquids, not necessarily involved with work, that you may have some interest in. We don't normally cover that. We consider it somewhat of a luxury to cover all of the topics that we do. So if you have some time to look through that's fine. I certainly will not hold you responsible for it. But as you work through physics and engineering, you may contact some of those applications that you find in section 7 of chapter 7. And then, of course, after we finish the center of mass, or the centroid, we're going to talk about some review integration topics. Again, that should be fairly straightforward for everybody, just to get everybody back into the routine of working with the standard basic forms. And then from that, we will basically springboard into a new technique called integration by parts. So first, what I want to do is share my screen and just give you a brief introduction to the center of mass. These are this note, or this page, is right from your notes, lecture notes that I have posted online. And I just wanted to give you a couple of ideas about this without having to have you write furiously to get through all of this. The idea here is that we take a physics approach, and let me make sure that we've got good, let's see, here we go, good focus. It looks pretty clean. Here we go. There we go. Yeah, the lots of times the manual is not so good. I like to orient the document cam so I don't have to, I can keep the sheet of paper oriented. There we go. Let's see, let me move this up just a touch. All right. So when we talk about center of mass, we basically take the idea, and let me get rid of some of these lines too. There we go. We think of physicists, and I'm gonna have to click through all of this to get rid of all of them. So I'll get rid of all, there we go, cool. So we take the physics approach, and we just consider a point in the plane, and we consider a directed distance. Usually in physics class, it's called the moment arm, and we consider its length. And we have a mass here at the end of the moment arm. And so basically, when we consider a moment about a point, if we want to think of P as being the origin, we want to think of the measure of a tendency to rotate. So for instance, if this were existing in a plane, or actually we've got a plane and then consider 3 space, and we had a mass here, there would be a tendency to rotate. That is, you would think this would come down by the effect of gravity. And of course, if you had another mass, equal mass, the same distance on the other side, you would consider that a balanced system. So the center of mass is, or centroid, and when I keep saying centroid, what I'm talking about is that we may have a lamina or setup that has a uniform density, and we're going to assign that density to be 1. So we're going to think of a geometric center, and that's when we use the term centroid. But if I say centroid or center of mass, they're just interchangeable. So what we do, like a physicist would do, is that we think of having a bunch of masses lined up along some line, and we consider the point P the origin. And so what we do is we take the product of each mass times the distance from the origin. And here I've written directed, so it will carry a sign. You know, when you do standard deviation, you square the distances so that you don't absorb variations from the mean. Here we want to do that. So this is not, this is not statistics. So don't think that way. So we basically say, okay, well, we're going to take the sum of each of these products and write it this way, like we're in pre-cal. Now, of course, that's just a finite sum. Later on in the course, we'll consider more elaborate sums that are infinite and then talk about their convergence. And that'll probably be the most challenging part of the class. I don't know, students tend to like it, even though it is difficult. Now, what we want to do is consider a balancing point, so to speak. If we could find a point along the line where the actual system balances, and this is where we take into consideration a little bit of college algebra. So these are very simple calculations, and I just wanted to talk through this. So we consider a translation in some real number. We're going to call it x bar. Now, this is the notation we're going to use for the x coordinate of the center of mass in the plane. So I'm going to utilize this here. So what we want to do is translate the system. That is, we want to replace x sub I with x sub I minus x bar so that the system has no moment. That is the tendency, well, a zero moment. The new moment, as I've written here, is 0. We want the tendency to rotate to be 0. So we want to basically balance the system. So how simple is that? Well, it's very simple. So let me get rid of all the extra stuff here. And when we look at that, again, this is a finite sum, so it necessarily converges. It has a sum, so to speak. It has an actual value. Finite always converges. We'll talk about that later. So basically, we just use some basic ideas. We multiply this by the distributive law and then break up the sum into 2 pieces. So basically, what we want to do is solve for the x bar. Well, we see the x bar is independent of our index variable, so we factor it. And of course, we just remove each of these sums to separate sides of the equation. Okay, and upon doing that, we can divide by what we call the mass of the system. Notice this is very ingenious. Here, if we think of a bunch of discrete masses, m1 up to m sub n, this term just basically describes the system mass. That is, we add all of the point masses to get the system mass. And then, of course, we'll eventually replace this with an integral when we have a continuous distribution. So the idea is when we actually solve for x bar, what we get is the moment about the origin, which we defined up here, divided by the system mass. So when we see this, we're thinking, okay, that will be our definition for the balancing point, the actual center of mass. So again, we have the moment about the origin divided by the system mass. So this is what we call the one-dimensional system. And physicists actually had this very correct. You simply extend this to the two-dimensional case. And when we do that, I want to do a very simple example. notice in this particular motivation, notice what I've written here, theoretical motivation. I wanted to spend a little bit more time with this because this is actually critical to your understanding. We actually motivated the other topics that we have discussed in this chapter, but this one is actually very critical. There are times when additional treatment is necessary. So let's take this idea and move it into a two-dimensional system. Again, these are straight from your notes. And again, I didn't want you to have to write furiously with this. I want you to listen to me. You can take a few notes if you like. The idea here is that the last example would be easy to actually compute. And you'll have a WebAssign example like that. Very simple, general math type topic. Here, what we want to do is consider a two-dimensional system. And what I've done here is that we think about the plane as containing our point masses, and I have an M1 here, an M2, and then et cetera to an M sub n. Now, we take the same concept, moment about the x-axis and moment about the y-axis. Now, here's the important thing. For every mass that we have in the system, we have a coordinate pair. And this, again, defines directed distances to the respective axes. So for instance, this x2 here gives us the distance to the y-axis here. This y2 here gives us the distance to the x-axis in a directed fashion in that it carries a sign. We look at M1, we have the same setup. That is, x1 gives us the distance to the x-axis and y1 gives us the distance to the y-axis. So again, in a directed sense. So this basically tells us how we define the moment about the x-axis and the moment about the y-axis. When we think of x-axis, we think of balancing on the x-axis, and we need the distances that will be given by y. And notice I flipped these around to kind of motivate the idea that we use for the moment about the x-axis, the y sub I directed distances. So this would be the tendency to rotate about the x-axis. So this is so simple, it can sometimes be difficult. And if you've already had university physics, you're probably snoring at what I'm saying. But again, it's very important. So now with the same idea, we can also consider the moment about the y-axis, where we think of the distances to the y-axis relative to each point mass. And so the moment about the y-axis would be summing the products x sub I times m sub I, and the sum giving us the idea of tendency to rotate about the y-axis. So this n gives us a way to actually define the centroid or center of mass for a mass system, discrete system in the plane. We simply take, in this case, the x coordinate of the center of mass to be the moment about the y-axis divided by the system mass, just like we did in the previous one-dimensional system. And then we define the y-coordinate of the center of mass, or the centroid, to be the moment about the x-axis divided by m. This will never change. Let me repeat, this will never change. So if we tend to look at a continuous distribution where we flip the x and the y independent variables for reasons of ease of use, so to speak, we will always maintain this, but it may happen that the actual integral formulations will vary here, and we have to be very careful of that. There are times when we set up a particular system of equations that may be dependent on the independent variable that we choose, and this is actually one case where that happens. So what I want to emphasize here, the next topic will be the continuous distribution or the planar lamina, but I want to do an example. So again, just right here, normally what I'll do, I'll use an uppercase M here for the continuous distributions. But if I use an uppercase M or lowercase m with no subscript, that will always indicate the system mass. So as we have here, we have simply mimicked what we had for the one-dimensional system. Now what I want to do is a simple example having to do with this discrete system. And this is a WebAssign. So let's do that now. Again, having intuition about this will make doing the problems a lot easier. And a lot of you are very intuitive when it comes to engineering and physics anyway. So I'm just going to try to take advantage of that. Now, let's look at a discrete system. So I'm going to call this an example and just say discrete. When I say discrete, we're not talking about a continuous distribution. We're just going to talk about a system of point masses. And the way the WebAssign does this, it's very convenient. We'll have a point mass they will label as M sub I and give its mass. And then we will actually have the coordinate representation that will give distances, directed distances to the respective axes. So we're going to have a mass of, say, 2 grams or whatever. The units are immaterial here, just they're consistent. 1, 2, and 6. So those are our point masses. And then WebAssign gives us the actual coordinate pairs. We have a -2, -3. We have a 5, 5, X and Y. We have a 7, 1. We have the origin, 0, 0. And we have -3, 0. Now, of course, you could plot all of these if you like to just get a picture of it, but I don't think that's required. You saw the picture on our basic theoretical motivation, and that should be enough. And what we want to do is compute the center of mass, so to speak. Compute X bar, Y bar. Now, again, remember, if in WebAssign, and you all are getting really good at this, if the parentheses are already given in the printout of the problem, you don't have to add them. You know, my pre-cal kids don't seem to understand that, but that's okay. They're just getting used to this. Now, first, what we want to do is just remind ourselves that we need a system mass, which I'll just use uppercase M, and that will be the sum of all the point masses. So we have 5 of them, so I'll let I run from 1 to 5 of the M sub I. So we'll just write it down. This will be 2 plus 5 plus 1 plus 2 plus 6. Of course, that'll just give us an 8 plus an 8, which is a 16. Nice, easy arithmetic. We're not dealing with the horrendous fractions that often ensue when we do these integrals. And then we want the moment about the x-axis. So we're going to look at the products of the point masses times the y sub i's, the distances to the actual x-axis. So we'll go ahead and write these down. We'll just look at each entry here. So we're going to get a 2 times a -3. And then we have a 5 times a 5. And then we have a 1 times a 1. And then, of course, a 2 times a 0. And then a 6 times a 0. Nice. We love zeros. Zeros are fun. Okay, so now when we look at this, we're thinking, okay, let's just go ahead and add everything up. We get a net, well, let me go down here since I put my equals here. So we'll get a -6 plus a 25 plus a 1, and these two terms are 0. So this gives us a negative 6 plus a 26, which is 20. So we have a moment about the x-axis of 20, and we have a system mass of 16. And now we just need the moment about the y-axis. Again, I want you to get used to writing these down so you remember what they are. It helps you to fit your logic with all of these problems. So again, we have the mass, point mass, times the distance to the y-axis, which will be given by the x sub i's. So again, we'll run through these like we did in the previous step. So we'll have 2 times the negative 2 plus 5 times the 5 plus 1 times 7 plus 2 times 0, and then of course 6 times a negative 3. So this gives us a negative 4 plus a 25 plus a 7 minus an 18. So now, of course, if we look at this, the negative 18 and the negative 4 give us a negative 22 plus 25 plus 7. And of course, here, this will be a 3. And then the 3 plus the 7 will give us the 10. So very simple arithmetic here. So now, what's good about this is that it just sets the stage for the continuous distribution. Now we can use our definitions. That is, x bar, the x coordinate of the center of mass, will be the moment about the y-axis divided by the system mass. So this will be 10 divided by 16, which will give us 5 over 8. And the y-coordinate of the center of mass will be the moment about the x-axis divided by the system mass. And so our moment about the x-axis is 20 divided by 16. So again, in this case, we could divide by 4. So that'll be 5 over 4. So when we write the center of mass, we have 5/8, 5/4. Now, of course, the idea here is that this is very simple, but motivated with very much intuition and common sense. So what we want to do is we want to take this idea and breathe some life into a continuous distribution, kind of like we took the frustum and figured out, well, what was so good about the frustum? Well, it gave us a way to actually interpret the area of a surface of revolution. And that was ingenious. 2 pi RL, and boom, it's right there in the integral formula. So you never forget the formula. We're doing the same thing here. Now, what I want to do is move this back to the continuous distribution. That is, again, these are from your notes, and I wanted just to give you an idea of where these definitions come from. It looks a whole lot more complicated than it is. It's really not complicated at all. Let me make sure I got the good focus. Excellent. And let me get just a little bit more light here. I don't want to, you know, flush it out so you can't see it, but I think that's a little bit better. I don't want the pencil to become, you know, invisible, so to speak. So what we want to do, and this is, let me, before I do this, let me just give you some terminology, ladies and gentlemen. When we think about a thin plate, and all you biology nerds, those of you that want to get into the medical field, become doctors and nurse practitioners, or get your master's degree in nursing and run a nursing program at a major medical center, things like that, you will have planar laminas that will sometimes consist of maybe living material, living matter. Maybe you're an engineer and you will have a planar lamina that consists of some chemical composition, say that you're working on at LyondellBasell. And so the idea is we think a planar lamina is just a thin planar piece of negligible thickness. But the thing is that it has what we call a mass per unit area, and we're going to use rho as that mass per unit area, like a mass density, so to speak, just like we had with the water, where we had the 62.4 pounds per cubic foot for water, or 1,000 newtons per cubic meter. Same idea here. We're going to call it rho. I think we used rho before. Maybe we should try another Greek letter. But this is what we're going to talk about. And just so this makes sense with what we talked about with areas, we're going to say that our planar lamina will be bounded by continuous curves and then possibly vertical lines. So this is what I want to talk about here. So we're going to think of our lamina in this particular case as being bounded in the upper sense by the curve F and bounded below by the curve G, and then of course the vertical lines x equal A and x equal B. Now we're going to consider the mass density in this particular case for what we're doing now to be uniform. That is, it will be uniform throughout the lamina, and that will be how we will run all of these for now. Later on, there may be a problem where we will consider that the mass density will vary relative to X. Remember, everyone, that the way we're setting this up, all of these centers of mass and centroids are tied to a coordinate system. The coordinate system is imperative here. So when you're thinking of a center of mass, you must have what you call an origin. So you've got to have a point of reference. So just remember, when you do these, the origin is extremely important. If you don't know where the origin is, your center of mass doesn't make any sense and your readers won't know what you're talking about. So now what we want to do is, considering that this is actually a uniform lamina of uniform mass density, we want to just basically talk about moments, just like we did in the discrete case. But first, I just want to write over here what we would think about as the mass of the system. Notice that if we take this partition of the integration interval A to B like we have here, we can look at the ith subinterval. And so we can think about just finding the area bounded by these curves. So once we compute the area, then we can actually multiply the actual area by the mass density, and that will give us the mass of the system. So this computation over here should remind you of what we did in section 1 when we found areas. The only thing we're doing is hitting it with the rho. Otherwise, it's exactly the same. And of course, if we let rho be 1, then it is the area. So this is easy. This is the easy part. Okay, so now what we want to do is we want to think of this strip here, and we want to think of the mass of the strip. Okay, so you know this is what we had here. When we think of the mass of this particular strip, we think of the actual length times the width, which we have here, multiplied by the mass density. So we call that the m sub I. We would need to do this for every strip in the partition here. Now we're thinking of moment. Well, let's do the easy one first. Let's do moment about the y-axis. So we think, you know, what's the distance in this particular case to the y-axis? Well, when we think of the Riemann sum, it would just be the distance here into this particular subinterval. We'll just call it c sub I, since it could be any element in that particular subinterval. We haven't been doing a lot of this, but I wanted to do it for this one. So this one's really simple. We just get m sub I times the c sub I. That is the directed distance to the y-axis. Okay, and now let's do the one that's a little bit more complicated, but not much. If we take this strip here, we want the directed distance to the actual center of mass, or excuse me, to the x-axis. But we want to think again of the center of mass of this strip. Here we could cheat and just use c sub I and not even think about it. But when you look at this strip of uniform density, we could balance this strip right at its midpoint, okay? So we use the midpoint that you learned in high school geometry. You just take the two y coordinates here and you add them and divide by 2. Again, so simple, it's difficult. So again, when you look at this, we say, okay, well, the midpoint right here will be the distance to the x-axis, and that'll just be this, f of c sub I plus g of c sub I divided by 2. Just like you were doing the midpoint to find the vertex of a quadratic function relative to its x-intercepts. It's the same thing. That's what I teach my pre-cal students to do. So now, in order to actually get formulas, we want to let the norm of the partition go to 0. Now, Professor Ron doesn't like a lot of extra stuff. And when you look in the book, they keep all of this factored, which is insane. So basically, this is just a difference of 2 squares. So I'm going to write it as f squared minus g squared in the limit. And of course, we have the 2 in the row, which gets factored as a constant. So that gives us the moment about the x-axis. So there's a formula right there. And I've got a little summary page that I'm going to show to you. And then, of course, with the moment about the y-axis, we have the distance x times the f of x minus g of x. So these formulas are easy to remember if you think about how we actually did this computation here. And that's why I'm going over this, because students are like, you know, I don't remember these formulas, Professor Ron, they don't make sense. And I said, well, you need to think about how we actually derived all of this. And again, this is just a motivation for a definition. So again, you will see these factored in the textbook. That is a waste. This is an identity. This is a difference of 2 squares. So go ahead and write it this way to save yourself the trouble of having to multiply this, which is, again, a waste of time and just a way to make additional mistakes. And then, of course, when we think about the moment about the y-axis, we just have the x times the f of x minus g of x. Now, one thing that I want to point out here, if we're doing an example where we actually make this rectangle for convenience horizontal, then basically the mx and the my, the moments about the x and y axes, flip-flop. The definition of x bar and y bar are still the same, but these flip-flop because now the rectangle will be horizontal. And so these formulas will actually flip. The idea here is this motivation here is dependent on how we've set up this rectangle. So this is where students often come to grief, and I'm telling you this now, we'll do an example involving this. So more about that later, but just note that this is more focused on the actual orientation of this strip. In the previous problems, you just basically interchange the x and the y and no problem. Solve for x if you have to, solve for y. But here, this is kind of more material when you think about this. So that's a little difficulty that we didn't have in the previous problems. Now, what I want to do is just give you a summary page. So this is basically what I did to kind of summarize everything. We have what we have that from the previous discussion. That is, we've got the one-dimensional case here where we started, the moment about the origin, and then of course the balancing point, so to speak. And then we have the discrete in the plane. Again, we have the moment about the x-axis, moment about the y-axis. And then we have the thin layer or plate, the planar lamina, bounded by curves. So again, sometimes like when you did the cross-section method, the base of the solid was a curve that was easy, like a circle. You're always grateful for that because that meant a much simpler analysis. But we will always think of our lamina as being bounded by curves. And of course, this will be where we have the x-axis, the x variable as independent, where f is greater than or equal to g along this interval of integration. And then, of course, we have all of these curves, the vertical lines and the f and the g, as I've noted here. And then, of course, we get the mass of the system. We get the moment about the x-axis, the moment about the y-axis, and then the definition here mimics the definition here, the same thing. So you can see that in the continuous case, there's more work to be done. The discrete case is fairly straightforward. The continuous case means that we have to compute 3 integrals. Now, of course, it might be the case that we have some very nice symmetry and we can maybe cheat a little bit, but I don't want to do that in general. I want us to be able, for instance, if we make a decision that, okay, it is clear that this is the case, then that's fine. But sometimes it's good just to go ahead and work through the routine and say, oh, okay, that's an odd function integrated over a symmetric interval. The answer is 0. So again, just remember when we do the continuous case, we have these 3 computations that must be computed in order to determine the center of mass or the centroid. So let's do an example. Again, these problems are just like what we've been doing. We just need to make sure that we keep everything organized. Now, the first one, we'll start out a very simple region just to get our feet wet. And this is a problem that actually can be generalized. So we're going to always start out with a lamina. And in this case, it is bounded by the following curves. A very simple example, y equal 1/8x, y equals 0, and x equals 8. And the assumption will be uniform density, mass density, uniform density rho. And we want to compute center of mass. Now, lots of times problems will be done where they just assume that the uniform density is 1 and you forget about it, but maybe that's not a good idea. Let the density rho absorb just in case you're doing a problem where it might vary and then you don't develop terrible habits. So for instance, this is easy. Let's just go ahead and get a little picture of this. I don't think you need it, but again, we're accustomed to doing this. So we've got the y equals 0. And of course, we have x equal 8. We'll be a little bit flexible with our scale. Now, of course, we have a 1/8 here. So we'll just mark off 1, be a little bit more liberal with the scale on the y-axis. So we have our, well, let me put this here. Here's our x-axis, and here's the y-axis. And so that'll give us this point here when we substitute 8 into here, and of course get a line. So we'll just, again, this extends indefinitely, but we see that we get this nice triangular region, which again, we can actually generalize the centroid of a triangle. So this makes a good example from which to start. Now, again, notice here, we have our 8 and our 0. And so x, again, the analysis here is simple. Sometimes we have to work a lot harder. Our interval of integration will be from 0 to 8. And now, if you will, we can just take an x here in the interval of integration and draw a rectangle. Now, what's nice about this is that the variables work very well in x, so we don't have to worry about any major changes. So in this particular case, we can set, if you will, f of x equals 1/8 x, and g of x, of course, is just 0. Okay, we will, again, we are grateful for that. That certainly makes our computation simple. So again, if you want to use the notation from the formulas, that's fine. You can adopt your own, but since we've been using the f and g, we'll stick with that. So now this implies that the mass of the system, if you will be rho 0 to 8, and we'll have f of x minus g of x. So this will be 1/8 x minus 0 dx. So of course, this is an easy integral. So let's just go ahead and factor rho over 8, the integral 0 to 8 of x dx. So add 1, divide by the new power. So we get x squared over 2, 0 to 8. Now, if you will, just go ahead and factor this over. That is, just multiply 8 times 2 using symbolic computation. And then, of course, we have times 8 squared. Now, of course, one of the 8's absorbed, and that gives us 8 rho over 2, or 4 rho. So that's the mass of our system. So let's go ahead and compute the moments. So it doesn't matter which one we do first. Let's do the x-axis moment. Again, remember, when we do the x-axis moment, we're using the midpoint formula because we're taking the distance to the x-axis, which involves that. So you can think of the midpoint being right there. And then, of course, the y-axis involves just the x. So this will be rho over 2, 0 to 8. And then we'll have our f squared minus our g squared. So I'll just, again, this, I think maybe what I'll do here, let me use a bracket because I've got too many parentheses and then they all look the same and it's maybe a little bit harder to read. So I'll go ahead and do a bracket. So I'll take my f here, which is 1/8 x, and I square it using Professor Ron's version because waste is waste, ladies and gentlemen. And then, of course, 0 squared dx. So this will give us a rho over 2 integral 0 to 8. Of course, the 0 squared is just 0, and we get 1 over 8 squared. So let's just say x squared divided by 64 dx. Again, just squaring this, squaring the 8, squaring the x. And then, if you will, this will give us rho. We have 2 times 64, the integral 0 to 8 of x squared dx. And so now, add 1, divide by the new power. I'll move this down. So we have rho 2 times 64. And then we have x cubed over 3 evaluated from 0 to 8. So this will give us a rho. We have a 2 times a 64 times a 3. And of course, the lower limit just gives us a 0. So we're just left with 8 to the third minus 0 to the third, which again is 0. So now what we see is that the 64 absorbs one of the 8s. So we get 8 rho 2 times 3. And then, of course, the 2 absorbs into the 8 to give us a 4 rho over 3. So that'll be the moment about the x-axis. Again, very simple calculations. It just depends on how complicated F and G are. So I think you'll enjoy these. And of course, you'll do this again in physics. Now, the moment about the y-axis will just be rho 0 to 8. Now, of course, now we're thinking of this. So that reminds us that we need the factor x times the f of x minus g of x. So you can see how very dependent this is upon the orientation of the rectangle. The orientation of the rectangle decides how these formulas look. So this is something we haven't seen in the previous cases. Okay, in the shell method, it was always the case that the strip was parallel to the axis of rotation. In the disk method or washer, it was always the case that the strip was perpendicular to the axis of rotation. This is not the case here. So you have to be much more careful when you work these problems. We did not encounter this in the previous problems. So now we have f of x minus g of x. So we have 1/8x minus 0. So all of these integrals are very similar, ladies and gentlemen. They're just minute differences. So that's why you have to be very careful. So again, we have the mass density, we have the distance to the y-axis, and then we have the f of x minus g of x. So this gives us rho 0 to 8, and this will give us a 1/8 x squared dx. So we can factor the 8. So we get rho over 8, 0 to 8, x squared dx. It's interesting when you're doing these arithmetic calculations like you found on the test, you really do have to be careful with your arithmetic. And I was very pleased with your work. The arithmetic that you build confidence in doing in this class will pay off in the future. So now we get rho over 8, and we add 1 divided by the new power. So we get x cubed over 3, evaluation from 0 to 8. So now we can go ahead and write this as rho 8 times 3. And then we just get, again, 3 copies of 8. But of course, the 0 cubed is just 0, so we can just leave that out. So now you see that one of the copies of 8 absorbs in this particular case. And let's see, notice in this case, this will give us rho times 8 squared over 3, which will give us 64 rho over 3. Now again, this is the moment about the y-axis. So now what we can do is apply the formulas. The x-coordinate of the center of mass will be the moment about the y-axis divided by the system mass. Now what I usually tell my students to do so you do not come to grief is to look at it this way. Go ahead and write down the moment about the y-axis as you normally would. And then invert the mass. Don't write a complex fraction. That, again, is a waste of time, unless you're just, writing a textbook. And so now the rows absorb, and we have the 4 into the 64, which will give us a 16. So that gives us a 16 over 3. And then for the y-coordinate of the center of mass, we have the moment about the x-axis divided by the system mass. So we go to the moment about the x-axis, which is 4 rho over 3, times, we just reciprocate the mass divided by mass. And of course, the 4 rows absorbing, we get 1/3. So what we're seeing here, this is a more, this reminds you of the more general formulation. So we see that the X bar, Y bar, in this case, it has the thirds in it. We get what, 16 thirds, 1/3. So again, this formulation for center of mass is very intuitive and very elegant when it comes to the continuous distributions. That is, we have a very nice way of now figuring out the center of mass for regions that don't possess symmetry. When the regions possess beautiful symmetry, we can intuit the center of mass or centroid just using the geometry. Common sense, so to speak. But when that fails us or that's not available to us, we have to just utilize the integrals. Now, what I want to do is an example that utilizes a discrete system. I think you'll find this in the WebAssign, and then we'll look at an example where the orientation of the rectangle changes. And I wanted to give you this example that I've worked out because there's a nice picture that we need. Okay, now this is, I had a honors class in Cal 2 one time. This was like about maybe, I guess about 6 years ago, where they made these models. They had these really strange regions, 4 of them, and they computed, they did this exercise and made their models, and the presentation was superb. The model was perfect because the young man who was the leader of the group could take the pencil and put it at the center of mass that they computed and balance it. So it was amazing that their honors presentation just took a topic that was somewhat dry and they gave it some life. So I was very impressed with that. When I changed offices, however, I lost the model. And now, of course, that our offices are being renovated now, I don't have much of anything left, but that's just life. Now, here's what we have in this particular case. Now, I'm sorry my circle looks more like an ellipse, but this is how the problem is given to us. Basically, you have some really beautiful symmetry here. We're given that the square portion has a mass density of rho, okay? And then we're given that the circular portion has a mass density of 2 rho, that is twice this, okay? Now, what I've written here is compute center of mass, and what I've said is treat as a discrete system. And you're thinking, oh, okay, so you know how the physicists say, okay, well, treat this particular planar object as a point mass, where the point mass is denoted by its center of mass. So when you've got this nice uniform square area, and this is what I was talking about before. Here is the origin. Notice this is completely dependent upon the way the axes are set up. So if you don't have a set of axes for one of these problems, then you need to make sure you put one in, because your computations won't make any sense. And as an engineer, and as a physics student, you'll just put the origin wherever you want it for simplicity. So the way the WebAssign problem is given is, here's the origin. So you have this nice square here that basically has an edge of 12. So we've got a 12 here and of course 12 here. Well, when you look at this, the geometric center is right there. There's the geometric center. So over here, I've got point mass at 6, 0. There's the geometric center right there. So we think of this as a point mass. So we think of all of the mass of this particular square area as being concentrated there. That's how you do these problems. You're thinking, oh, I've got to do some fancy integrals. No, that's why I'm doing this, because this confounds students in Cal 2 to such a degree that I don't understand it. And now for the circle, we continue. Notice the center of the circle is at 18, 0, and it has a radius of 6. So again, we're going to concentrate all of the mass at 18, 0. So there's our second point mass right there. So when I say treat this as a discrete system, there's mass 1, there's mass 2. Now, in order to complete the problem, let me share this with you. This is important, and I'm doing this in this amount of detail because you need it. Now, what I've done in this particular case is first, in order to get the center of mass, we need the mass of each of these portions here. So notice, in this case, we have an area here that we can compute for the square, and we have the mass density of rho. The area will just be an edge squared. So we have rho times 12 squared, which gives us 144 rho. Again, we think again of this mass, boom, right there, concentrated right there. So again, when you've got this nice, beautiful symmetry, you deal with this as a discrete system. Each geometric object corresponds to a point mass. We notice in this case, we just have 2. I need to move every time I need to see. I said 2. Can you see the 2? I don't know here. There we go, 2. I can't see my face, so I'm not really sure what you all are seeing. But I don't want my face all over the shared screen. Now be sure to do that so you can see what I'm pointing at. Now we can look at this and say, okay, well, let's do the same for the circle. Again, we've got a mass that's concentrated at 18, 0. And so we're thinking, okay, now here, the mass density is 2 rho. The area will be pi r squared. The radius here is 6, so we get pi times 6 squared, which is pi times 36. And of course, 2 rho will give us a 2 times the 36, or 72 rho pi. Now, in order to compute the center of mass, we need the system mass. So basically, we have to add this mass to this mass. So we get M, uppercase M, will be 144 rho plus 72 rho pi. And of course, we do the Professor Rahn approach, which is to factor until we can factor no more, which is to extract the common factor of 72 rho, which we get here, leaving behind 2 plus pi. So there's our system mass. So we can say system mass. Now, what I want to do is do exactly what we did before, but you see I flipped this around, so forgive me. Here we have the M sub I. I'll just go ahead and add this in. And here we have the X sub I, Y sub I. So I'll go ahead and add this. So we have the point, which gives us the directed distances where we find the masses and the associated masses. So first, we want to do the moment about the x-axis. So we need the distance to the x-axis, which is given by the y-coordinates. Well, that's easy. And that's when you think, oh, we could have used some symmetry, Professor Rahn, but let's just do it anyway. So we have 0 times 144 rho plus 0 times 72 pi rho, which we have here. 0 plus 0 is 0. Now, intuitively, you knew that to be the case. But again, let the algebra show you the way, confirm what you think intuitively. And now, for the moment about the y-axis, again, here's the y-axis. The distance to the y-axis will be given by the x-coordinates. So we have the distance here, 6, times the mass, 144 rho. And then we have the distance here, 18, times the mass, 18 times 72 pi rho. And notice here, we've got common factors again. We just use what we have here, the 72 row, or excuse me, 72 pi, and the 72 pi that we have in here, we're going to remove. Well, there's no pi here, so let's just go ahead and take these out. We'll take the row, and we'll take the 72 here. Notice this is just 72 times 2. If you don't factor, you get a big mess, and we don't want our calculations to look untidy. And so now that will give us the 6, the 72 row, and what do we leave behind? A 2, and then of course we have a 3 pi, because again we extract the 6 here, that leaves us a 3 and the pi. So this is nice and clean. So now notice, in order, well, we know what the y bar is going to be, but let's just go ahead and compute this. Now, this, you think a WebAssign problem like this, where you've got all of these nice continuous lamina, oh, I've got to integrate. No, this is set up so you don't have to integrate. This is set up for you to utilize the symmetry that we have present with the geometry. Consider this to be a discrete system. You will find great use for this in physics. Now, the x coordinate of the center of mass will be the moment about the y-axis divided by the system mass. So our system mass right here, 72 rho times 2 plus pi, we just move here. And then of course we've got this beautiful copy here of the moment about the y-axis, which is 6 times 72 rho times 2 plus 3 pi. Now, here's what we have. Notice all of the unfortunate stuff basically just absorbs. The 72 rho in both cases absorbs, and we're left with 6 times 2 plus 3 pi, and then the 2 plus pi. Now, of course, this is exact here. If WebAssign asks for an approximation to maybe 2 decimals, you can use this. But again, you do all of your calculations exactly, then you approximate at the end. No approximations at all until the end, and that's only if WebAssign asks for it. This is what I prefer, but again, you know that in some cases, and here's another thing I may make you aware of. You know this when you test. If the little bar, the little palette comes out and it asks for an approximation, you can do either. If the little palette comes out and you can use the symbols, WebAssign will take either. So that's something that gives you flexibility when maybe you're not interested in the approximation. Now, of course, for the y-coordinate of the center of mass, we have the moment about the x-axis divided by the center, or the system mass. And so we go for our moment here, which is 0 divided by something non-zero, which is 0. We know, again, with the symmetry here, that it's intuitive to us that the y-coordinate must lie on the x-axis. But again, don't just assume that. It seems, you know, from what we have here, that this supports what we would consider to be the y-coordinate of the center of mass. And so when we compose this, we have this. History has shown me that this problem deserves a little bit more attention due to the fact that I would get questions about this problem, and I would check the login information for my students. And by the time they got to the last try, they were just typing in gibberish because I think they were ready to throw their computer out the window. Do not do that. One of my best students, like 3 years ago, had a meltdown with this problem. And I said, please don't do that. This is very straightforward. Just think about it in terms of a discrete system. And when I said discrete, the light bulb came on. So again, when you have an initial reaction to a problem, don't be upset if you have to vary it. That's okay. That's the scientific approach, and we do that in math all the time. Don't think that you only do that in your physics or chemistry lab. You do that in math all the time. Okay, now what we want to do is to consider a situation where we have a horizontal rectangle. So let's do an example of that. Now, like I said before, there's an example where you actually compute a formula for the center of mass of a parallelogram that is coordinatized with general coordinates. And so what you find is that it's much easier to look at the problem with a horizontally oriented rectangle. So why do we choose that as opposed to the vertical? Because if we're trying to find the mass, that would allow us only to utilize one integral. If we have to write 2 or 3 integrals because the upper and lower curves are varying, that's too much work and introduces too much room for error. So here's an example where we're actually going to flip things around. This is a fairly complicated example, and I wanted to cover it so that you will have the knowledge of working with rectangles that have different orientation. So here we have a lamina of uniform density. Lamina of uniform density rho, and we have, and I'll say bounded by. We've got 2 curves that are written in the independent variable y. X equals negative y, and another quadratic function. You all don't like the quadratic functions where the y is independent. I know this, that you just don't prefer them, but that's okay, they exist, so we're stuck with them. So again, when we think about this, this would be an excellent problem, as you recall, for area between 2 curves. This is a great problem for that, and it would make a good review problem, which we're going to see. Now, what we want to do is compute the center of mass. So I'll say compute x bar. I'll just kind of shortchange this y bar so I don't have to write so many words to save a little bit of space. So let's go ahead first and consider the intersection. Notice this will be a quadratic function, or actually parabola, that opens to the left because the leading coefficient is negative, and we could see the y-intercepts easily, but let's just look here, intersection. And let me do a little bit here. There we go, clean that up a little bit so you can easily see it. So the intersection will be, we have, if you will, and again, when it comes to intersection, we see that a lot of this stuff absorbs and it makes for an easy computation. So we get negative y squared plus 5y, just equality of ordinates, equals negative y. And so now we can just transpose. So this will be a negative y squared plus 5y plus a y gives us a 6y. And then if you will, you can factor the negative y. And that'll give us a y minus 6 equals 0. Now, of course, by zero product, we get y equals 0, which wasn't a surprise, and y equals 6. So if and only if y equals 0 or y equals 6 in this case. So now when we look at this, that'll give us 0, 0. And then of course we have a 6 and a negative 6. So if we put in 6 for y, x is negative 6. So that gives us the intersection point. So that's going to help us to draw it, just so we know which curve is to the right and which curve is to the left, so to speak. Move the cursor out of the way. So the picture helps us to get a visual of what's going on. Nothing wrong with that. Your future mathematicians and STEM professionals, so you give presentations. It's nice to have some some visual aspects. So what we can do, and I can draw this so it's easy to read. Let's just say we have like a 1, 2, 3, 4, 5, 6. And let's see, we'll spread this out a little bit on this axis. 1, 2, 3, 4, 5, and then a 6. So spread this out a little bit more. -6 and a 6. So about eyeball this about right here. And now, if you like, this gives that we also know, again, we've got 0, 0, so we've got this point here. So that at least gives us what the line's going to look like. That gives us this easily. So let's go ahead and draw that. Oh, let me write this to the side and draw this. So this will be our y, or excuse me, x equals -y, right there. Now again, when we look at this quadratic function, let's analyze that a little bit. We have x equals -y² plus 5y. Let's go ahead and factor it. We can find the vertex just for grins. We don't need it. But of course, the intercepts we can already see. This will be a negative. So we get y² minus 5y. Half of -5 is -5/2. So we square that. That gives us a 25/4. So add it and subtract it. Just basic complete the square, which you all have become professional at, and for obvious reasons. And so now here, that's a perfect square. So we get the negative y minus 5/2 quantity squared, and then the negative plus 25/4. So that's 6 1/4. So that's where the vertex is, of course, 5/2. So we could say, so vertex, let's see, 25, 4, 5/2. So let's see, there we go, about right there, 5/2, 2.5. And I'll do this the same. So 1, 2, 3, 4, 5, 6, 7. So about right there. So just kind of eyeball it. Again, this is not a work of art, just easy. And then of course we have the x-intercepts of 5 and 0, which you can easily see. So I'll go ahead and draw this. Like that. So, you know, the part about these problems is not so much that this work is difficult, it just takes time to do. We don't necessarily have to have the vertex, but now you can see the reason for this. Vertical rectangles here would be a nightmare because you have different upper and lower curves. So that would not be the way to go. So what we're going to do is we're going to orient the rectangle the way the problem is given to us. We've got the 0, 5. So, oh, well, that here. And then, of course, notice, let me go ahead and shade all of this. I wanted to note the intercepts here for the y-intercepts for our curve. But let's go ahead and shade everything. So you can see the actual lamina. So now, if we think about this, we can take the horizontal rectangles, and of course, the y would live between 0 and what, 6 up to here. And that would cover all of this. So this implies y lives here. This is a really good example, and maybe probably the most difficult one in this section, except for the derivation for the parallelogram, but that's easy because you just have a bunch of letters to deal with. So 0 to 6. And so now if you took a y here, you just draw in a little strip. Right there. So this is where the orientation of the rectangle is to make things easy. And then of course, now we can see the left curve. Now, if you look at it this way, this is what's so great about this document cam. I can't do this with a Wacom tablet. I'd be losing my mind. So I'm glad for the document cam. So if I flip it this way, I've got like an upper curve and a lower curve. Or this way, I have a right curve and a left curve. So now we can think of f of y as being the quadratic. So this will be 5y minus y squared. And the g of y will be the left curve, which is just negative y. So when we write these and when we think about it this way, it's a whole lot easier to actually work through. So this right here kind of gives us what we need for this problem. So the sketch simply helps us to believe. I mean, once you do the intersection here, you kind of have the interval of integration. And then you pretty much know which curve is to the right and which is to the left. So this picture is just to add a little bit of extra intuition. Again, not completely necessary, but I want you to see how this rectangle changes things a little bit. Now let's go ahead and get the mass of this system. So we have our row, integrate from 0 to 6. So we're going to have f of y minus g of y. So we have 5y minus y squared minus negative y dy. So this gives us row 0 to 6. And so we have 5y minus y squared plus a y. So we can add. So this will be row 0 to 6. So let's write the negative y squared first, and then plus a 6y. So these are easy integrals. Easy, but arithmetic. So we have row, so add 1, divide by the new power. So this will give us a negative y cubed over 3 plus 6y squared over 2. And we want to evaluate from 0 to 6. Now, I'll say this, sometimes we can use the arithmetic of the problem and factor the arithmetic since the lower limit's 0 here without having to do too much work. So this will give us what? Row negative y cubed over 3. And then, of course, that'll just be a 3y squared. And then we can do common denominators once we've evaluated. That's just a personal choice as you do these problems. Notice the lower limit will annihilate both of these, so we don't have to worry about that. So we get row, and this will be a negative 6 cubed divided by 3 plus 3 times 6 squared. Now what we can do is just get a common denominator of 3. So this will be a negative 6 cubed. And we need a 3 here, so that'll give us a 9 times a 6 squared. So now we can factor the common factors. So first we're going to get a row divided by 3, the 3 here, and then of course the 6 squared will come out. And then that's going to leave us with a negative 6, and then, of course, plus the 9. So we get rho over 3 times 6 squared. And then, of course, we get a 3 here. Well, hallelujah. The 3 is absorbed, and we get a 36, or 6 squared times a rho, which is 36 rho. Well, don't believe it. We actually got a non-fraction. Well, you know, rho could be anything, but we don't see the fractional state of it since we're using what, symbolic computation. Now, so now what you're seeing here is that this problem right here is like an area calculation. This is 7.1 here. That's all we've done. And this would maybe be overkill for that, all the extra stuff. But again, just wanting you to see this. Now, here's the important part. Let's go ahead and do, and I think what I'll do the moment about the y-axis first. Now, I want you to think about this before I write this down. Think about this and use the logic that I've tried to share with you. Think about where the midpoint of this thing is, right there. Now, we want the moment about the y-axis, so we need the distance of that little point mass to the y-axis, and that's where we have to use the midpoint deal. So that's where the rho over 2 comes in when we actually derive these formulas. So this is what's going to change. So you have to think about this when you write these formulas down. So we're going to get a rho over 2. So I'll just write here. Let me just say here. Strip is horizontal. So that's really all you need to think about when you write this formula down. So now we've got, and remember, we get the f squared minus the g squared because Professor Ron doesn't want to write a bunch of extra stuff. So we get 5y minus y squared minus negative y squared dy. So now we'll just do the arithmetic, and of course, limits of integration would also be good since we want to get, you know, a number. So we have rho over 2. Slide up a little bit. 0 over 6, and so we'll expand the binomial. So this will give us 25 y squared minus, and now we have a 5, a negative 5, so that's a 10 y cubed with a negative. And then, of course, we square this term. This will give us plus y to the 4th. And then we have minus y squared. Now, what's interesting about this particular problem is that all we had to do was make this small change, and now the problem's just like everything was before. So let's go ahead and finish this. So this is rho over 2, and we'll collect terms. So I'll write the y to the 4th first, and then minus 10y cubed. And then, of course, we have a 25y squared minus a y squared, which is a 24y squared. So now we can add 1 divided by the new power. So we have rho over 2. So this will give us y to the 5th. This reminds me of the problem I did with the cross-section method, but at least we don't have to worry about the lower limit giving us a extra work because it's a 0, thank goodness. That makes a big difference. Then we have minus 10 over 4, y to the 4th, plus 24 over 3, y cubed, between 0 and 6. So now at this point, we can go ahead and reduce, and then we can do a common denominator once we evaluate, if you like. Now, I will say this, go ahead and reduce this a little bit first. So we have rho over 2, y to the 5th divided by 5, minus, that'll be a 5/2, y to the 4th, and then of course plus an 8 y cubed. And then we can use the arithmetic to factor. So now we get rho over 2. And so this will give us a 6 to the 5th divided by 5 minus 5/2 times 6 to the 4th plus 8 times 6 to the 3rd. And then, of course, the lower limit annihilates everything, so that's a relief. So let me move this up to another sheet of paper. Now, to make the arithmetic a little bit easier, what I'm going to go ahead and do is get a common denominator. So we have rho over 2, and just go ahead and we'll just use a 10, obviously, and then we'll factor it. So we have a 2 times a 5. Slide that up just a little bit. Move my Wacom pen out of the way. I'll make sure you can see that. Okay, so now we need a 2. So we have a 2 times a 6 to the 5th. Here we need a 5. So we have minus 25 times 6 to the 4th. And here we need the 10. So that'll be plus an 8 times 10 times 6 to the 3rd. So now we have rho over 2. Now, if you look at this, we've got some 2s. We've got some 2s in things to make things just a little bit easier. But again, that's your choice. I like to make things simple. Let's see here. So first, let's just go ahead and take out the 10 downstairs. 2 times the 5. And then, of course, we've got a 6 to the 3rd in every one of these things, and we have more, but I'll worry about that in a minute. So 6 to the 3rd. And that leaves us a 2 times what? 6 squared minus a 25 times a 6 plus 80, basically, 8 times 10. So this will give us, if you like, rho, and we have a 6 times a 6 times a 6, and we have a 2 times a 2 times a 5, downstairs, factoring that. And then if we look here, additional stuff in here, we've got a 2 here, we've got a 2 here, and we've got a 2 there. So another 2. So that leaves us a 6 squared, which is a 36. And remember, this is just a 2 times a 3. So that leaves us with a 3 times a 25, so minus 75. And here, this is just a 2 times a 4. So that leaves us with a plus 40. So now a lot of this stuff goes away. Well, not all of it, but some of it. So again, these are 2 times 3, so we get a rho and the 2, so that leaves a 3 behind and a 3 behind and a 6. The 2's being gone, the 5 surviving. And then of course I've got this 2 right here. I can't forget that. That lone 2 right there. So we'll put that right there. And then, of course, now I've got easy arithmetic. This is a 76 minus 75. Factorization is the way to do this. I teach you this because I know you haven't seen it done this way before. I learned this way as an undergraduate, and it stuck. And I had some professors that were some of the most brilliant minds in the world at Carolina and at A&M. So I think they knew what they were talking about. So that's a 1. But now notice here, we have a 9. We've got a 54 times a 2. So this is 54 right here. So 54 times 2 is 108. So 108 rho over 5. That unfortunate number is we computed to be the moment about the y-axis. Okay, so now let's do the moment about the x-axis. Now let's go back here and let's think about what we have to do. This is going to set you up for the parallelogram rule. Now notice when we want the moment about the x-axis here, we need the distance to the axis in this case, and that will be given by the independent variable y. So we've got the y formula here. So we see how they flip again. But just think about the rectangle, strip is horizontal. So this will be rho 0 to 6. So we have y, and then we have, well, let's go back here. Remember, f of y is 5y minus y squared, and g of y is negative y. So we have 5y minus y squared minus negative y. All the minuses are important. So we've seen this before, but it's good to do it again. So we get 0 to 6, we get y. And so of course we have the 5y plus the y. So that's going to be a negative y squared plus 6y dy. And so now when we multiply, we have rho 0 to 6. So we have a negative y cubed plus 6y squared dy. Now, just like before, when we did the previous problem, we had more stuff, or we had more unfortunate powers. But again, what we're seeing is that this type of calculation mimics what we've done in all the previous types of problems. And this is actually even more lengthy because we have 3 integrals that we have to do when we have these continuous lamina, especially when it's devoid of, well, this is really devoid of any symmetry that we can, utilize in this case or exploit. So we're kind of stuck. So now what does this give us? So we have rho, add 1, divide by the new power. So y to the negative 4th over 4 plus 6y cubed over 3, 0 to 6. So we have rho. Now this will be a negative y to the 4th over 4. And then of course this will absorb to give us a 2y cubed 0 to 6. So now what we can do is go ahead and substitute, and then we'll get a common denominator and factor it. Probably easier to do it with the numbers. So we've got a negative 6 to the 4th over 4 plus 2 times 6 to the 3rd. Of course, the lower limit annihilates everything, so we're done with that. So let's get a common denominator. So we get rho. So we have a 4. So we get a negative 6 to the 4th. And here, this will be an 8, or 2 times a 4, so that'll be an 8. Let me just go ahead and write it this way. 2 times a 4 times 6 to the 3rd. Now we can see easily that we've got a 6 to the 3rd. Let's go ahead and get rid of that, then we'll finish up the factoring. It's better to do it that way so you're a little bit more confident about what you're doing. So we got the 4 here, and then we've got a 6 to the 3rd and everything, and then we're going to pull out the 2. So we have 6 to the 3rd. And now that leaves us with a negative 6, and here plus an 8. Well, that's easy enough anyway. We won't have to worry about factoring that. That's pretty simple. So now, if you will, we have a row. So we have a 6 times a 6 times a 6, and we have a 2 times a 2, and of course that's a 2. So if you like, you can do, let's just do it this way. We have a row, so that's going to be a 3 times a 3. Let me put a little dot in between these so you see it for what it is. Not a 33, but 3 times a 3. And then times a 6 times a 2. So again, the 2's absorb into the 6's to give us 2 copies of 3, and we have the 6th row, so we got the same thing again. That's a 9 times a 6, which is a 54. So we get 108 row. So what I wanted to point out with this problem is that this is going to give you the, I'll summarize this and we'll compute the center of mass. This is giving you the recipe to deal with horizontal rectangles. Because remember, the way this is set up, we have distances to the respective axes, which depend upon how the strip or rectangle is oriented. So this is really important and something that often slips through the cracks. So remember this as this example when you're working on the formula for the parallelogram. So now, by definition, x bar, what's that going to be? Well, that's going to be the moment about the y-axis divided by the system mass. So the y-axis moment, that was one that we did first. That's right up here, right? 108 rho divided by 5 times the mass. Now the mass, remember here, 36 rho, right there. So reciprocate that. Now, one thing you're going to notice here, and this may not be completely obvious, notice the 108. If you divide by the 6 here, that gives you a 1 to 48, so you got an 18 there. So if you like, this is 6 times 6 times 3. So that's useful. So now we get what? 36 times 3 rho divided by 5 times 36 rho. So the 36 rows, well, the rows absorb in the 36s, and that leaves us with a 3 over 5. And now for the y-coordinate of the center of mass, this is the moment about the x-axis divided by the system mass. Now we did the moment about the x-axis right here. So this will be 108 rho times 1 over 36 rho. Well, we've seen that before. That's just going to give us a 3. So now, if and only if, the center of mass, x bar, y bar, will be 3/5. Now, of course, depending on how WebAssign generates your numbers, you'll get a similar problem, but the numbers will look different. It just depends how the numbers generate. So now when we have 3/5, so we can just kind of go right over here and mark this off, 3/5, 3. And of course, I didn't do this justice. This is not Rembrandt at all, but so here, so 3/5, so 3 about right here. Say 1, 2, 3, and then 3/5 about right there. So that's kind of like a guesstimate. There's our center of mass right there. So this is kind of after the fact. 3/5, 3. Now here's what's important, ladies and gentlemen. and this is important, the moment about the y-axis and the moment about the x-axis, the formulas change, but the formulas here, of course, are still the same. It just depends on how the rectangle is oriented, how the strip is oriented. And so now we've got a, you know, relative idea of where the center of mass is. I mean, of course, if this is, you know, you've got a model here, you want to build this model and scale it, and got some nice equipment to build it. You've computed the center of mass, so you could take your pencil and locate the center of mass and walk around balancing it like a magician. Again, I still remember the group that was able to do this, and it's unfortunate I did not keep that model. I don't think I think I intended to keep it. That it got lost is unfortunate. When I moved offices from N7 to N10, I'm almost sure I had it with me, but somehow it got lost in the mix. Okay, now there's one other formula or one other idea that I want to share with you. It's called the theorem of Pappus. Now, and I've got something in the lecture notes I want to share with you. You're going to be able to prove this in Calculus 3. So I may talk to my boss and see if I can go ahead and do maybe next semester do a Calculus 3 course. It's a fun class, and after this class, you really get to enjoy going back to a lot of Calculus 1 techniques. Now, again, like I say, we'll be able to effect a nice proof of this using computations that we can do with double and triple integrals in Calculus 3. But this is called the theorem of Pappus. And I also have a nice example of a problem that we've already done that will be a nice explanation of a previous problem that we did via the shell method. Now, this is culture. Notice I put culture here. There's a WebAssign problem with this, but this is not a linchpin. This is not the most famous problem that we end up doing in this class, but I do want to make you aware of it. And then we get to Cal 3, if we have time, we'll effect a proof of it. And so again, so many of these beautiful results were known to the ancients that did not have the benefit of calculus, but yet had the intellect and the intuition to formulate these theorems that were later proven to be absolutely correct. We're still trying to prove everything about Newton and Ramanujan, but of course, every time the work is done, everything they have come up with is correct. So here's how the theorem of Pappus goes. It says, let R be a region in a plane, and let L be a line in the same plane, such that L does not intersect the interior of R. What that means is that L can touch the boundary of R, but it cannot reside any points in the interior. It can't delve into the interior points away from the boundary. So that is something we need. Then this is where what our discussion has been today will make sense. If R is the distance between the centroid, remember that's another name for the center of mass, especially when we're talking about geometric constructions of R, and the line, then the volume of the solid of revolution, ring a bell, solid of revolution, formed by revolving R about the line L is this. And you're thinking, that looks like the shell method, Professor Ron. That looks like the volume of a frustum, except we've replaced L with A. And you're thinking, my goodness, why didn't we have this formula when I was knocking myself out with the shell method in the torus? So where A is the area of R. So the torus example I've got in lecture notes right here, and I want to share that with you. So again, this is a nice cultural problem, and you know, you can throw rocks at me later, but again, we had a very nice example of this with the torus, where we took a circle that is oriented at the center here, the origin of the system. We have a vertical line, x equal 5. Now, what's interesting about this particular problem is that we have beautiful symmetry here. So relative to this coordinate system, the center of mass of the circle, again, we're considering this to be of uniform density, is right at the origin, okay? So we've got this circle of radius 4, and we have a line x equal 5. So now what we see, if we think about the formula, the distance to from the center of mass to the vertical line, the axis of revolution, again, is 5. So we have, if we go down here, we have r equal 5. So I'm sorry, let me move this up. We have r equal 5 using this formula. And then all we need is the area of the actual geometric object. So this has a radius of 4. And so we get, in this particular case, and I'm doing the example that we have with the torus here. Let's see. Let me check something here. So we had the 1/2 2 pi. I'm checking. Let me check something here because I want to make sure this is exactly the way I want it to be. Yeah, notice here I don't need that 1/2 because I'm not using the shell method. Let me fix that. I've got it written correctly up here. But let me get rid of this. That's just a typo. And I was thinking about the symmetry when we did it with the shell method. So there's no 2 there. So that's just 16 pi. Good old math always tells us when we make mistakes. So let me go ahead and put this here. So that'd be twice, so that'll be 160. This is not in your lecture notes. I just added this last night. So now what we see here is if we compare this to the torus method, the method that we use to find the volume of the torus with the shell method, we see that this is much simpler. So again, area of the region to be rotated, which is this, 2 pi, and the distance from the center of mass to the axis of revolution, right here. And we get the answer. Now, again, if we notate what we would have done with the torus method here, that is the shell method, we see that all of this is involved in the same computation. So now what I want to make a point of is if we look at this and we think about what we're doing here, then we get the same computation. And that's where my factor of 2 dropped out. So if we think about the shell method, let's just go ahead and look at this as a shell method. We've got our strip here, and we're going to integrate from -4 to 4 this particular curve. Okay, and so this is where we need the additional copy here. That is, we need the additional copy to get the entire circle here. Now notice when we actually do this and we get the distance from here to here, we've got our copy of 2 right here. So the actual height of the strip will be 2 times the square root of 16 minus x squared, which takes us from here to here. And then we integrate from -4 to 4. There we go. And now the distance in this particular case from the strip to the axis of revolution, as we computed before, is 5 minus x. Well, this distance right here is x, so we have 5 minus x. And so when we substitute all of this, we get 2 integrals like we had before. Notice the integral over here is the odd function integrated on the symmetric interval. That's 0, which we saw before, which you did in your quiz. But now if you look at this and you kind of pull everything apart, you can see what's going on here. Notice the piece here that we see right here. That gives us the area
of the actual region, which is A, the 2 pi we have here, and the 5 we have here. So embedded in this formula here is actually this formula. So this is basically a special case of the theorem of Pappus. Now, what I want to share with you here is to say that when we find a new way to actually do a problem, we need to see where there's some consistency here. We need to see how do the two examples and the two procedures relate, and we can, again, deconstruct this and see that we get the same formula here, the 2 pi RA, 2 pi RA. So what I want you to do is just to go back to this problem in your quiz and in your homework and think of it in this light. Work the same problem, but now work it with the fact that you know what center of mass is and you know what the theorem of Pappus is. And again, it should remind you of the area of a frustum when we thought about that. So again, what I want you to think of this is as a culture type exercise where you have a theorem from the ancients that really is a calculus result, but was actually determined without the use of calculus. So again, I wanted to share that with you and just give you an idea of how we can actually interrelate the types of problems we've been doing in this section. Now, like I said before, there is one example in your WebAssign where you actually find the center of mass of a parallelogram. And so what I want you to do in that particular case is apply the horizontal rectangle. So here's a hint. You'll see this written up in your notes, but don't go straight to the notes. I'll just give you a little hint here. I'll cover up all the work. When you actually set up this problem, set up a horizontal rectangle and work it out as we did in the problem that we did previous to the theorem of Pappus. Try that out. And if you get stuck, this is in your lecture notes. Now, that does it for our excursion into the applications of the definite integral. So what we want to do now is go back, and we're going to spend some time on this for our next lecture, go back and spend some time on some review integrals. And we'll just do maybe one before our time ends. So if you want to go ahead and look at section 7 of this chapter out of interest, be my guest. I will not hold you responsible for that on the test. So what I want to do is just a couple of exercises. Well, we'll do several, not just a couple, but just some review exercises of some basic integral techniques. And that's, you can go ahead and start working on 8.1 even before you work on 7.6. So this will be 8.1, which will be basic integration techniques. So basically a recap of everything we've done since Cal 1, basic integration techniques. And maybe a few ideas that we just need to review. So we'll start out with a simple one. You had a nice one like this on your test with the exponential, which was miscellaneous substitution. Here's an example. So we have 5. Sometimes when we do these problems, we don't even need a fancy substitution. We just need some algebraic manipulation. Now, most of the problems in this section will be indefinite integrals. So don't forget about your definite as you do your problems with the center of mass. But this is basically reviewing techniques. Now, when you look at problems that involve the exponential, you have your standard e to the u du, which is just e to the u plus a constant. But when you have examples like this, often you need to do some algebraic manipulations in order to write this in a form that you can anti-differentiate. So in this case, this is a good example. Use a convenient factor of 1. Use a convenient factor of 1. So the convenient factor is going to be e to the negative x divided by e to the negative x, because that's going to render this into what I think will be a du over u. So we have 5, 3, e to the x minus 2, e to the negative x. It's like almost like a conjugate method, but not quite. We don't have a difference. So we're thinking this will be an identity. That is, this will be an identity based upon all values of x for which it is well defined. And e to the negative x is defined for all values of x. So we're going to write an equivalent expression for this. So algebraically, we're in good shape. So this will be 5 e to the negative x. What's an identity? An equation that is true for all values of the variables for which it is defined. And then, of course, we have e to the x times e to the negative x. That'll give us a 1. So we get 3 minus 2 e to the negative x dx. Now, when you look at this, this is much more user-friendly than this. I mean, we don't have a substitution here, and then you're thinking, do I need to try miscellaneous? Now, I'm not saying this is the only way to do this. Clearly, these techniques are not unique. But now you can see that the 5 is just in the way, and then we can rig this. So for instance, let's go ahead and think about this, making this into table-ready form. So we have a 3 minus 2 e to the negative x dx. And then we have an e to the negative x. Now, of course, we're going to think about this as a u substitution. So we will think u is equal to 3 minus 2 e to the negative x. And then du, of course, taking the derivative of 3 is 0, and the derivative of the exponential will give us a negative 1 times the negative 2. So that'll be a 2 e to the negative x. Now, again, the calculus of the natural exponential is so easy, we think we're cheating, but we're all ready to go here except for the factor of 2. So with the factor of 2, of course, we have the dx there. The math tells on me, just like it did with the theorem of Pappus. The problem is ready to go if we just go ahead and insert the 2 and then pay for it. So let's make this table ready. So this will be 5 halves. And now we have 2. Go ahead and bring the dx right beside the exponential factor. So now we've got the u and the du. That is, now we have the form du over u, which is the natural log form. So we're good to go. So this will be 5 halves natural log, absolute value of 3 minus 2 e to the negative x plus a constant. So when you look at problems like this, this is not a problem that requires a fancy technique of integration. You know, we often find ourselves, once we learn new techniques of integration, that we want to use them. But then we get back to problems that we could do before we learned those techniques and somehow think that these new techniques must apply to the previous example. And that's not necessarily the case. So what I want you to do, and we'll talk more about this on Wednesday, what I want you to do is to start working on these, and let's just kind of refresh our memory of all of the techniques that we have utilized to this point. That is table ready. We've got the inverse trig forms. We have some miscellaneous substitution, which we reviewed on the first test. And so just to kind of give ourselves a time to assimilate all of the techniques that we're aware of. And then once we feel comfortable with that, we're going to go ahead and step into the major technique called integration by parts. Integration by parts is probably the most important technique past the chain rule. The formulas that you can utilize derived with parts it's astounding. It is a major technique
and one that will allow you to integrate objects that were never before at your disposal. So we will start with that and then move through some very nice techniques. And then of course, as you get to the university and you take more advanced mathematics or even advanced engineering classes, you'll probably learn more about the hyperbolic functions as they relate to new types of integrals, elliptic integrals, and the gamma function. So we have to start by making sure we have a very secure foundation with the fundamental techniques, and then we can always expand from there as our classes require us to do. All right, so today, thank you for your attendance. I think that you're going to find the Center of Mass Calculations kind of fun, but I'm sure once you're done with them, you'll be done. You'll be ready to move on. And if you have time, go ahead and start working on the basic integration techniques. And I'll go ahead and get up a quiz that will be due next week that will cover through 8.1. And of course, we'll have our office hours this week. So if you need some additional help or want to work on some of these problems, please take advantage of the office hours. Everyone have a good day, and thank you for your attendance.
Thank you. Have a great day.
You too.